Okay, everybody, so today we're going to be expanding what we can do with our material balances to reacting systems. Right, so far we focused only on non-reacting systems. And in non-reacting systems, mole balances and mass balances are interchangeable, right? Because they're related just by the molecular weight, right? So every mole balance is exactly, it's not an independent equation for every mass balance. But when we work on reacting systems, the reason why we have to work in mole balances is because all of our chemical reactions are written in terms of moles, right? That just seems to make the most sense overall. So I will go over very, very briefly some background on chemical reactions, section 4.6 in the Felder book, and there's also videos online that give us a bit more detail. So I'm going to do a really rapid overview of chemical reactions. Hopefully this is content that you have already seen before. So a general chemical reaction, right, we can write A number of A plus B number of B. Oftentimes I'll write reactions as an equal sign because this is really an equilibrium process. The reaction can move forward, it can move backwards, but you can also see it like a forward arrow and a back arrow. But you just have to note that every reaction, there really is no such thing as a truly irreversible reaction. Everything can be reversible to some extent. C, and D, D. And of course, right, I can have many more components involved in this process. One thing that's really important about chemical reactions is, can I vary the concentration of A and the concentration of C independently? Using only the reaction. I cannot. Because if I'm consuming A, I have to be forming C. So when we look at this process here, we think there's 1, 2, 3, 4 unknowns. Right? But there really isn't 4 unknowns. Because the concentration of A, B, C, and D are all linked through this chemical reaction. And so the complexity of doing chemical reacting systems is that you can't vary the species independently, and it's a bit trickier for the degrees of freedom. And that's why the handout that you guys have has degrees of freedom for the different methods that we're going to be using to solve this analysis. So as the example that we're going to be running through in this class involves the Haber process, which is the synthesis of ammonia. And so I'm going to call this A, so I don't have to write out NH3. This chemical reaction is basically the basis for why we can have, I think it's about 8 billion people on the planet, right? So if this reaction hadn't been discovered how to be done efficiently at high pressures and high temperatures over a catalyst, we wouldn't necessarily have enough fertilizer to be growing the crops that we have. So it's a very important reaction overall. What I want to introduce using this process initially is this term, the stoichiometric coefficient. So the stoichiometric coefficient is how we can mathematically convert this chemical reaction to something we can insert into equations. And we use the Greek letter nu. So the stoichiometric coefficient, for those of you who have seen it, who's seen the stoichiometric coefficient? Okay, what is the stoichiometric coefficient for nitrogen?
1.
Is it 1 or is it something else?
-1.
It's -1. So the stoichiometric coefficient for nitrogen is -1. The stoichiometric coefficient for hydrogen is -3. And the stoichiometric coefficient for ammonia is +2. Now the reason why we differentiate between the positive and negatives, it doesn't matter if I write this reaction this way or the opposite way. If I use the correct procedure where everything on the left-hand side is negative and everything on the right-hand side is positive, I can generalize all of my equations, which means I don't have to worry about which is positive, which is the forward and which is the reverse reaction, because it's all taken care of mathematically here. And we'll do this as a demonstration using equilibrium constants. So, chemical equilibrium is governed by an equilibrium constant. Now, in chemistry classes, you saw this a lot with a acid dissociation term, right? In general, we're mostly going to be focusing on chemical reactions of ideal gases. And so how we can write this is the pi, this is the product sum, it's multiplying everything together, is equal to the mole fraction of species I raised to the stoichiometric coefficient power. So you don't have to worry about where this equation comes from, just how to apply it. So you can either calculate an equilibrium constant if you know the mole fractions, or if you know the equilibrium constant, you can calculate the mole fractions at equilibrium. So how we write this product sum here raised to the stoichiometric coefficient, this would be y of ammonia squared divided by y of nitrogen divided by y of hydrogen cubed. Right? We have stoichiometric coefficient of -1, which means it goes into the denominator. -3 goes into the denominator. So if we look at this equation, we would think there are 3 unknowns and 1 equation. We can't solve this. So we need some way to relate between our mole fractions so that we can condense all of this into 1 unknown. Then we can solve the system. Have people seen this type of a calculation before? Equilibrium calculation. Now, this is something that I'm sure most people have done in their chemistry class with acids, where you had maybe H plus A minus and HA, right? So that's your products, you're dissociating your acids, and your reactants are your acid itself. So how we accomplish this is we introduce a term called the extent of reaction. Now, conventionally, the extent of reaction is noted as the Greek letter xi, which I think is the hardest one to write, which is unfortunate, so it's kind of a squiggly thing. So I get very creative when I write this on my work, right? But this is typically the Greek letter that is used for the extent of reaction. So we define, and this has units of moles. So we define the extent of reaction as the number of moles of species I at some time. This could be the equilibrium, this could be at the outlet of a reactor. It's just the number of moles of species I at some period that we're investigating the system. Minus the number of moles of I initially, that's what this little knot here is for, divided by the stoichiometric coefficient of that species. The mole fraction is written as the number of moles of species I divided by the summation of all the moles in species I. So what we do is we rearrange this expression to make it look like this. And we get the mole fraction is n I naught plus stoichiometric coefficient, extent of reaction, divided by summation of the moles. So if we were to take this expression here for the mole fraction, but as a function of the extent of reaction, we know, if this is an equilibrium problem here for the Haber process, for example, and if we know the initial number of moles in the system, we know all the stoichiometric coefficients because it's defined based on the reaction itself. We only have one unknown in the system here, right? And that is the extent of reaction. So what the extent of reaction communicates to us is how much have we gone from the left-hand side of the reaction to the right-hand side of the reaction. So one extent of reaction means that 1 mole's quantity of material moves from one side to the other. So that would mean if 1 mole of nitrogen is reacting, 3 moles of hydrogen are reacting, and 2 moles of ammonia is formed. That constitutes 1 mole's worth of the extent of reaction. So let's do this in an example then. So we need to get an expression here for the mole fraction of all 3 of the species, assuming that we know what the equilibrium constant is. So the number of moles of hydrogen is we're going to apply our formula here, right? So this right here, this is Ni. So we have some initial number of moles of hydrogen minus 3 times the extent of reaction. For nitrogen, we have some initial number of moles of nitrogen minus 1 times the extent of reaction. And for ammonia, it is plus 2 times the extent of reaction. Now, if we were to add all of these together, the total number of moles will be equal to the total number of moles initially plus how much changes as you react in the system. So we have minus 3, minus 4, plus 2 gives us minus 2 times the extent of reaction. So this tells us that the number of moles in this system is not conserved. As we react, right, we're consuming 4 moles and we're forming 2, and that's characterized here mathematically in this extent of reaction format. So we're going to evaluate the mole fraction using this formula, Ni divided by the summation of Ni. This is what this is here. That's the summation of Ni. So the mole fraction of hydrogen would be equal to the amount of hydrogen initially minus 3 times the extent of reaction divided by the total number of moles minus 2 times the extent of reaction.
Could you say that one more time?
Okay, so we are taking this part right here is N of H2 divided by the summation of all the moles. So I'm taking...
So that would be the mole fraction.
Exactly. So I'm taking the number of moles of hydrogen written as a function of the extent of reaction and dividing it by the total number of moles.
Okay.
So this gives us the mole fraction. Because if we think of it, it's not a simple process what's going on here, right? So if I feed the system with a stoichiometric ratio, yeah, question?
I was just going to ask, are you trying to put the mole fraction in terms of function of the extent of reaction?
Correct, yep.
Okay.
That's the goal. Because then we can write this expression here where we have 3 unknowns, and over here we only have 1 unknown, right? The initial number of moles in the system, that is given to us in the problem statement. Right, so if we go back over here and we say we have a stoichiometric ratio of nitrogen and hydrogen, that means if I have 1 mole, let's say 25 moles of nitrogen, that means I need 75 moles of hydrogen. So the mole fraction of nitrogen would be 0.25, the mole fraction of hydrogen would be 0.75. But if I start the reaction and it moves forward, that means I'm decreasing the total number of moles, right, which is the denominator here, and I'm modifying the number of moles of each of the independent species. Right, so it makes sense that this expression for the mole fraction of any one of the individual species is somewhat complex. Any questions? Yeah.
And we know that we are decreasing the total number of moles because at the bottom of that, in the top left-hand corner, yeah, right there, that equation.
Yes.
Because it's minus 2 times the extent of reaction.
Correct.
You know, the total number of moles is decreasing.
Yes, so every time the extent of reaction is positive, we're losing 2 moles. But we could also have a negative extent of reaction as well.
And that would mean the process is going in reverse. Right?
Exactly.
Okay.
Right? In the real world, I'm not going to be feeding 100% of my reagents and 100% of my products is 0, right? I might be feeding a mixture of products and reagents. And so it might be that the reaction actually goes backwards. Or maybe you're doing a real balance with 50 different reactions, right? In oil refineries, You know, you can have a matrix of reactions that are hundreds or thousands of different reactions going on, and you don't necessarily know how reactions 1 through 75 affect reactions 75 through 150. Some might be going forward, some might be going backwards. But if we stick with this nomenclature here, it doesn't matter. Right? I could have done exactly the same thing and written this completely in reverse. Right? I could have written my reaction as ammonia dissociating into nitrogen and hydrogen, but all the positives become negative, and it still works out just fine. All right, so let's continue in this procedure here. So the mole fraction then of nitrogen is the number of moles of nitrogen. So N2 initially minus 1 extent divided by the total number of moles, N naught minus 2 times the extent. And then lastly, Y of ammonia. We have our expression there. So now the last step is we take all 3 of these terms here, input them into our equation for equilibrium constant. And I know it's ugly, right? It's not a trivial equation, but it is still just one equation and one unknown. So we can solve for this directly. How does everyone feel about that? In general, you'd be given an equilibrium constant, but it is possible for you to calculate the equilibrium constant as well. So let's say you did this reaction, waited a really long time, measured the composition. You could then use that information to calculate the equilibrium constant. Okay. So that is how we do equilibrium expressions. Now I'm going to go through a couple of quick definitions, and then we're going to jump into an example of doing a balance. So the reason why we do this is because now if I were to provide a reacting system balance, I don't have to tell you what the reaction does to completion. I can say the reaction goes 50% to the equilibrium completion, which basically means then you would have to solve for the equilibrium state, scale the extent of reaction by a factor of 1/2, and then you would go about doing the balancing. And we're going to show the balancing now in a second. But a couple of definitions. Yield. This is the moles of a desired product. Divided by the moles of an undesired product. So in your homework example on 6, you're trying to make ethylene epoxide out of oxygen. So your desired product would be ethylene epoxide. In a more complicated problem, an undesired product would be CO2, right? You're just burning the ethylene. Right? That's an example of what the yield is. Selectivity. This is moles desired. Oh, sorry, this is selectivity. I wrote this. Oops, my bad. So in yield, the top is moles desired divided by moles This is, okay, so the yield is the moles of the desired product divided by the moles formed in a perfect world. So no side reactions, no complications, 100% to equilibrium, all that jazz. Selectivity is when you have 2 potential products, right? So in this case, you could have A going to B and A going to C, right? B could be the desired product, C could be the undesired product. And so your higher yield would be moles of B divided by moles of C, if that was the particular example. Right? And lastly, conversion. This is moles reacted divided by moles fed. Now Now mathematically, we can typically write this n in minus n out divided by n in. So conversion is kind of I call it like a dumb piece of information, right? All it relates to is the moles coming in versus the moles coming out of the system. But it doesn't care about what reaction it's participating in or any of that. It just says, oh, some of it's missing. So it reacted somehow. So this is how it's written here. So I can never remember this equation, so I kind of always work it out in my head. Right? So if I feed in a bunch of, let's say, nitrogen to this Haber process here, right? And I want to say it's 100% converted, right? That means this term here should be 1, which means that n out would have to be 0, right? Because if n out is 0, n in over n in, that's just 1, right? That's 100% conversion. Now, if there's 0% conversion, that means nothing reacts, and something's gone catastrophically wrong in your system, right? How do we get 0 out of this equation? Well, that's if n in is equal to n out, right? That gives you 0, and that gives you a conversion of 0. Yes?
Sorry, on the yield it says moles desired and it's moles.
It's moles formed in a perfect world. So no kinetic restraints, no equilibrium problems.
This is ideal.
Just totally like if you could magically make all of the product that you wanted. That's what the yield is. All right, so what we're going to be doing now is we're going to be going through 3 different ways to balance a reacting system. And on your handout, you see there are 3 different ways we can do the degrees of freedom. We're going to start off with the one that you should never use, except under rare circumstances. That is so the 3 ways we're going to solve this balance problem are a molecule balance, which is probably the way that you are most comfortable thinking about it, but it is the way that is the least helpful in the class. We're also going to do an atom balance, and then we're going to use the extensive reaction approach. So we're going to be using this Haber process here as our example. And the problem statement is going to be that we are feeding our reactor with a 100 moles per minute total feed. And it is going to be in a stoichiometric ratio, right? Meaning that you have just the right amount of nitrogen and hydrogen to react perfectly to completion. So this amounts to 25 moles of nitrogen per minute and 75 moles of hydrogen per minute. And out of the system, we have an unknown flow rate of nitrogen, unknown flow rate of hydrogen, and an unknown flow rate of ammonia. The other piece of information that we're going to be given is 50% conversion. Now, in general, if the system is more complicated, we'll specify conversion of which species. But since everything's in stoichiometric ratio, the conversions are going to be the same, right? Because these molar balances or molar flow rates are not independent. But if you had an excess of one reagent versus the other, then we would have to specify conversion of which species. But in this case here, it doesn't matter because everything is linked together. Hopefully that makes sense. Okay. Now on your sheet, you have sort of like my advice of when to use different balances. And if you look at molecular species, which is what we're going to start off with first here, it says simple systems with one reaction, but then don't. Basically, the only time you really are forced to use a molecule balance is if you don't know what the species are. Or maybe you don't know, or it's really, really simple. But this is, I assure you, this is probably what most people would think about if they tried to do the problem on their own. So we'll do the degrees of freedom really quickly. So if you look at our sheet, it says number of unknowns minus independent atomic species. Let me grab this here. So molecule balance. So let's do degrees of freedom. So if you look at our sheet, number of unknowns, we have 1, 2, 3 unknowns, the 3 outlet flow rates. So 3 unknowns minus number of independent atomic species balances. How many of those do we have? Wait, oh, sorry, no, I'm looking at atomic balance. Sorry. I was looking at the wrong one. Plus number of independent chemical reactions. How many is that? That is 1. Minus independent molecular species. We have 3 molecular species. And minus the number of design specifications. How many of those do we have? 1. Minus 1, so that gives us 0 degrees of freedom. So we have enough information to solve this problem.
That design specification is the 50% conversion, right?
Bingo, it is the conversion. So, how we do a molecule balance, and this is going to be distinct from an atom balance, is we're doing our general balance equation, but for each molecular species. So our general balance equation is in plus generation minus out minus consumption is equal to accumulation. All right, now let's start off with a nitrogen balance. What is my balance, right? Let's take our general balance equation and simplify it. What terms go to 0 in the general balance? So we have stuff coming in. Are we generating any nitrogen?
Yeah.
No. Out, do we have stuff coming out? Yep. Are we consuming nitrogen? Are we accumulating anything? No. So our balance turns into in is equal to out plus consumption. So mathematically, we write this out. We have 25 moles, and I'm going to drop the per minute because it's going to be on everything. Moles of nitrogen is equal to our unknown, n dot n2, plus the rate of nitrogen consumption. Right, and this is where things get a bit tricky. So before we tackle this problem, let's just keep going with our balances. So, I hydrogen balance. What simplifies out here? It's exactly the same, right, as the nitrogen. So it's in is equal to out plus consumption, 75 moles of hydrogen is equal to our unknown plus the rate of hydrogen consumption. And lastly, let's do our ammonia balance. This one's a bit different. Okay, are we feeding any ammonia? Are we generating ammonia? Yep. Are we taking stuff out? Are we consuming any? And no accumulation. So in this case here, we have out is equal to generation. So our unknown is n dot ammonia, and this is equal to the rate of ammonia generation. So now the tricky part here is we have to relate between the rate of ammonia generation to the rate of hydrogen consumption to the rate of nitrogen consumption. And that's where things get a bit trickier. So what I'm going to use now is I'm going to use the 50% conversion to say that our N of ammonia is equal to 50 moles per, 25 moles. Right, if we had 100% conversion, we would be taking 100 moles of the feed and turning it into 50 moles of the product. We have half of that, which basically says that we're using our design spec to break into this right here. Right, so now we have checked this one off. So now we have a way to calculate what is the rate of ammonia generation, and now we have to relate that to all of these other individual terms. So this is how I work through molecule balances. So how I do it is let's do, it doesn't matter which one. We can do nitrogen or we can do hydrogen.
Can you explain what you did with 50% conversion?
Yeah, sure. So there's a number of ways we could do this. we could strictly apply the conversion equation, right? Where we have 0.5 is equal to n of, let's say, hydrogen in minus n of hydrogen out over n of hydrogen in. We could apply this equation here, and we could use it to figure out, which of these two are, or which of the, what's the outlet here, right? Another way we can think about this is we have 0.5 is equal to the trying to think. So I did this a bit hand wavy. I'm trying to put some math to it. So if I were to do this demonstration over again, I would probably enter in with one of these 2 points here, and we could do it that way as well. As it turns out, I wrote my example solving for this one first, and so it's a bit hand wavy. So we could do it this way here, where we use the conversion to calculate how much of the hydrogen out is. But another way to think about it too is we could also write this as 0.5 is equal to moles reacted divided by moles fed. And this is kind of the generalized way that I did it here in this example. We're feeding 100 moles and we're reacting, but it's a little bit trickier because you're reacting 4, but you're forming 2. So this is not the tightest example I've ever had, right? But conceptually, we can kind of connect the dots, right? Because if we had 100% conversion, we would be going from 100 moles to 50 moles. So a 50% conversion goes from 100 moles to 25 moles out. So again, it's a little hand wavy, but let's work through the example because we've got to get through the 2 other types before, because you need them for the homework. So if we were to apply the nitrogen balance then, and again, I don't recommend the molecule balances almost in any circumstances ever, because this is always going to be the issue. We have 75 moles equals our unknown, 25. 25 of nitrogen plus our unknown, plus the rate of nitrogen consumption, right? Now, I don't really know what this is, but I know in my reaction that my rate of generation of ammonia is 25 moles of ammonia generated, and then I need a conversion factor here. So for every 2 ammonia generated, I am consuming 1 and 2. So I take this term here, and that is my rate of nitrogen consumption. Because if we look at the units, we can put this over minutes, of course, too, right? 25 moles per minute of ammonia being generated. For every 2 ammonias being generated, we need to consume 1 nitrogen. So the units here are 25 over 2 nitrogens consumed per minute. And they work out. So if we were to plug this in, we can solve for the n dot n2 is equal to 12.5 moles per minute. I know this is unpleasant because molecule balances are innately unpleasant. We can do exactly the same thing for the hydrogen. We're running a bit low on time. This would be 37.5 moles of hydrogen per minute. Don't ever use a molecule balance if you don't have to. Right? Because the problem with the molecule balance is you have to deal with generation and consumption, and these things are not super trivial to calculate unless you're really, really meticulous. And as you can clearly see, I don't meet that criteria. Now, the 2 strategies that are extremely highly recommended are atom balances and extent of reaction. So we'll just do the atomic balances in our heads right now, just to save some bit of time. So Number of unknowns. We have 3 unknowns still, right? If we're looking at our degrees of freedom sheet here. Number of independent atomic species balances. What do we think that is? How many different atom types do we have in this Haber process? 2. We have nitrogen and we have hydrogen. Not molecular nitrogen, but atomic nitrogen and atomic hydrogen. Non-reacting independent molecular species balances. These are inerts, right? There's no argon or anything else floating around in there, so that's 0. And design specifications is 1. So we have 3 unknowns minus 2 independent atomic species, N and H, and minus 1 design spec. That gives us 0 degrees of freedom. So in an atomic balance, it is the same idea as a molecule balance, but we're not generating or consuming individual atoms. Right? So instead here we wrote N2 balance, right? That's a molecular species balance. In this case, I'm writing just an N balance. Right? Ultimately, I don't care how the nitrogen is bonded. I just need to know that the same amount of nitrogen that enters is the same amount of nitrogen that leaves. Right? Not N2, but N. So being fed to the system, I have 25, in this case here, right, our balance simplifies to in is equal to out. I don't have to worry about generation and consumption, which are these tricky terms to deal with. And the nitrogen balance is in is equal to out. So I have 25 moles of N2 per minute. For every 1 N2, I get 2 N. Right? So the nitrogen molecule has 2 nitrogen atoms in it. This is equal to what is leaving the system. I have an unknown N dot N2. And again, for every 1 N2, I get 2 N's. I have an unknown ammonia. For every 1 ammonia, I have 1 nitrogen. Is everyone following how I did that? So I'm keeping track of all of the different species that are potentially coming into the system and coming out, and counting how many of the atom type nitrogen is in it. 25 is coming in. That gives me actually 50 nitrogen atoms. Leaving, I have unreacted nitrogen, which has nitrogen atoms, and formed ammonia, which has nitrogen atoms. I can't solve this equation here, though. Yeah, question?
Where did you do the degrees of freedom calculation for the atom balance?
So on the sheet here, we just did it really quickly in our heads. I didn't write on the board.
Okay.
But yeah, so if we follow along on the sheet here, we can do it up real quick actually then. So if we have 3 unknowns, we have minus a number of independent atomic species balances. This is minus 2. So this is our nitrogen and our hydrogen. Number of non-reacting species is 0, so this is inerts. And minus 1 design spec.
And that's just
That's the conversion. Yep. That gives us 0 degrees of freedom. All right, so let's repeat this again, but this time we're going to do an H balance. So coming into the system, we have 75 H2. For every 1 H2, we have 2 H. Leaving the system, we have our unknown amount of H2. Again, it's 1 H2 gives us 2 H, plus we have an unknown ammonia. And what should I write here for my conversion factor for ammonia?
Quickly going
Sure.
back to the N balance.
Sure.
Why is it on the last part,
Mhm.
1 ammonia instead of 2?
So if we look at ammonia, the molecule of ammonia has 1 nitrogen atom in it. So for every molecule of ammonia, it takes with it 1 nitrogen atom.
So it's not dependent on the circulation.
Not at all. So the great thing about atom balances, I didn't even have to write this chemical reaction. You don't have to balance a chemical reaction to do an atom balance because you don't care. All you care about is how many molecules of which species coming out are there and how many atoms does it take with it.
So that means it'd be three hydrogens?
Exactly, yep. So for every one ammonia, it is 3 hydrogens. And then lastly actually no, this is it.
Two balances.
And so what we need now, we have 3 unknowns. 1, 2, 3, right? We don't know nitrogen, we don't know hydrogen, and we don't know ammonia. So we have to use our conversion to determine one of these. We could do it on the nitrogen, we could do it on the ammonia. So depending on the problem statement, you'll get one or the other. But let's say, for example, we were to insert here 25 moles of ammonia per minute, right? Then we can solve this expression, and then we can solve this expression here. Right? This is just simple algebra at this point onwards. And if you were to crunch the numbers and double check, hopefully I get the same answer. Atom balances are fantastic. They're especially useful for combustion reactions, which we'll talk about on Friday, when you're burning a complex fuel. Because when you purchase coal or crude oil or gasoline, we don't actually know what all the molecules are that are in it. All we know is what is the hydrogen content, what is the carbon content. We have no idea how it's bound together. So we actually can't write out a chemical reaction for it. We have to do atom balances on those types of processes. All right, any questions? Yeah.
Would you ever tell us to do like a molecule balance then?
So in general, I don't care which technique you use. I want you to use whichever seems to make the most sense. Some circumstances, you will be forced to use a molecule balance because it might be, I could say A plus B goes to C reaction in a reactor separator, right? And you cannot physically do a atom balance because you don't know what A, B, and C are, right? So that limits you a little bit. All right. So hold tight really quickly. We got to run through extensive reaction approach because you'll need it for your homework. Okay, so extended reaction approach, we won't do the degrees of freedom, but it works out to be 0 as well. Now, in the extensive reaction approach, what you're doing is you're introducing an additional unknown, right? And if you look at the extensive reaction approach here, it's got more terms for our degrees of freedom. So we are introducing an extra unknown, and that is the extent of reaction. But the goal is that that extra unknown makes it very easy to solve all of the other problems, right? So what we're going to do now is we're going to write out the balance exactly how we did it for the chemical reaction equilibrium problem, right? So the number of moles of hydrogen coming out of the system is just going to be equal to the number of moles fed. In this case, it's 75 moles of H2 per minute. And then we're going to have minus the stoichiometric coefficient 3 times the extent of reaction. Right? This is the same format of n of I is equal to n of I naught plus the stoichiometric coefficient times by the extent of reaction. So I have one equation and 2 unknowns. I've added in an extra unknown that wasn't there in my molecule balance and that wasn't there in my atom balance. Right? So I'm, in theory, mathematically, making it slightly more complicated of a problem. But it makes the solution extremely algorithmic. So then I repeat the process for nitrogen. It's 25 moles of nitrogen per minute minus 1 times the extent of reaction. That's just based on the chemical reaction we have. And then the number of moles of ammonia that we don't know is equal to 0 plus 2 times the extent of reaction. Now, I have 1, 2, 3 equations, but 4 unknowns, right? Because I've added in the extra unknown that is my extent of reaction. But what makes this simple is if I know that the number of moles of ammonia is equal to 25 moles per minute, and this is from the 50% conversion, right? Then I can solve for my extent of reaction. So the extent of reaction is equal to 12.5 moles. I take this and then I can solve all of my equations.
Sorry, could you show how you did that again?
Sure. Okay, so this term right here is from the conversion. So we did that at the beginning when the molecule balanced. So we're relying on this still. So if we take the 25, so we have 25 equals 0 plus 2 times the extent of reaction. And we solve for the extent of reaction, it's just 25 divided by 2. That means our extent of reaction is 12.5 moles. Technically 12.5 moles per minute. But since we've been truncating the minute. Yeah, question?
So if we're having an extent of reaction of 12.5 with this particular process, meaning we are getting 50% conversion, does that mean it's highly, like it's almost completely going the one way, or is 12.5 not very high?
12.5 is the net change. So since we've written the reaction this way and we have a positive extent, that means we're going from the left-hand side to the right-hand side, a total amount of 12.5 moles worth. But if I were to rewrite this expression saying 1/2 nitrogen plus 3/2 hydrogen equals 1 ammonia, this number would be different potentially.
So it is not, it doesn't tell you how likely it is to occur.
No, it just tells you what has occurred. So the likelihood of occurring is going to be related to more so the equilibrium constant itself.
Okay.
Right, but from here though, right, once we have the extent, but the thing is, if I were to rewrite this equation here, like scale it by a factor of 2 or divide it by a factor of 2, right, all of these different stoichiometric coefficients would change, which means my extent would change, but the end result would be exactly the same, right? And so from here, right, it should be straightforward. Each of these, you can just plug and chug the numbers, and you should get the same answer. Now, the last thing before we go is reminder of what a reactor separator looks like, right? A reactor separator has a mixer. Don't draw the mixing to go into the reactor. It has a reactor. It has a separator. It has a top and bottom stream of the separator. It has a splitter, a purge stream, and a recycle going back down to the mixer. If you draw this recycle going straight into the reactor, you're robbing yourself of a material balance, right? This mixer is an extra material balance that you can perform, or a system that you can do balances on. And if you draw it straight back into the reactor, you're robbing yourself of a system to balance, right? You're having to balance both the mixing process and the reacting process. So you'll need to remember what the reactor separator is here. And you'll have to go through and use the molecule, the mole, the atom balance, and the extent of reaction approach to solve some problems on this week's homework. So it's a bit rushed towards the end, but office hours are today. I don't exactly remember which time. Tomorrow, mine are from 1 to 3. So look at the homework, come to office hours, and we'll help you out.